The drilling site was silent. No engines, no workers, no movement. Only a narrow opening in the ground, still marked, still exposed. The drilling had stopped, but the site was never abandoned. After the drilling stopped, the borehole was not sealed. It was preserved, protected, and redefined. Under the Continentalis Teeth Bore program, the borehole was no longer treated as a finished operation. It became a working space, a vertical laboratory, extending deeper into the earth than any laboratory that had ever existed before. There was no drill bit, no cutting, no further extraction. Instead, measuring instruments were deployed. Long sensors, suspended by cable, were slowly lowered along the exact path the drill had opened earlier. They did not touch the rock to take samples. They were there to record temperature, pressure, subtle changes. Over time, meter by meter, the cable slid through gloved hands. The depth markings gradually disappeared into the opening. At a fixed depth, the descent stopped. Readings stabilized. Numbers were written down. Then the cable moved again. This was not a one-time procedure. It was repeated day after day. The borehole was no longer a remnant of physical intervention. It had become an active system. And from that moment on, the limit was no longer set by the drill, but by the cable that connected the surface to the depth below. At that depth, losing the cable would not mean bad data. It would mean losing the entire system forever. With each descent, the measurements went deeper than the instruments had ever been used before. The borehole was not just deep, it was extreme. Temperatures rose steadily, far beyond surface conditions. Pressure increased with every kilometer. The sensors were still functioning. The data was still coming back, but the environment they were entering was no longer neutral. The cable carried more than weight. Heat was conducted upward along the cable. Mechanical load increased with depth, and tension accumulated over distance. At great depths, even small movements mattered. Thermal expansion caused subtle changes along the length of the cable. Materials responded differently than they did near the surface. Nothing failed suddenly. There was no snap, no visible warning. Instead, subtle inconsistencies began to appear in the readings, not errors, but signals becoming harder to interpret with confidence. The sensors were checked, then recalibrated. The procedure continued. Each time the cable was lowered, operators watched the numbers closely, not just what they revealed about the Earth, but what they implied about the system used to reach it. The deeper the measurements went, the clearer one thing became. The tools were approaching conditions they had never been designed to endure for extended periods of time. Heat did not remain isolated at depth. It traveled upward. Stress did not stay confined to a single point. It distributed itself along the length of the cable. The borehole remained intact. The surrounding rock did not shift. But the weakest element in the entire system was no longer underground. It was the connection itself, the thin line linking the surface to the depths below. Logging continued, carefully, methodically. But from this point on, every descent carried a new question. Not how much more could be measured, but how long the connection could safely be maintained. At those depths, where heat was already being conducted upward along the cable, and mechanical load had begun to accumulate, the act of measurement was no longer passive. The Earth was not simply being observed. It was interacting with the system in real time. As logging continued under those conditions, the cable grew heavier, not only from its own weight, but from the environment surrounding it. Heat softened materials. Pressure altered tolerances. What had behaved predictably near the surface responded differently, kilometers below. At extreme depth, lowering the instrument was no longer routine. The cable could bind against the borehole walls. It could deform under sustained load. It could stop moving freely. In some scenarios, The risk was no longer imprecise data, but losing the entire measurement system inside the Earth. A stuck instrument, a severed cable, no recovery. The borehole itself did not need to collapse. For the operation to fail, everything depended on a single continuous connection. And that connection was being tested by the same conditions that made the measurements valuable. At that point, the role of measurement quietly shifted. It was no longer a question of what the instruments could record. It became a question of whether the Earth would allow those measurements to continue without turning the act itself into an irreversible intervention. The balance that had held during earlier logging was no longer guaranteed. Not because the drill had reached its limit, but because the environment had begun to impose conditions of its own. From that moment on, depth was no longer the primary boundary. Control was. Once the risk became clear, the response was not dramatic. There was no public announcement, no declaration of failure. But the way the borehole was used began to change. Logging was no longer treated as an open-ended scientific exercise. The number of measurement runs was limited. Only specific instruments were approved. Only specialists with direct experience were allowed to operate at depth. Procedures once designed for scientific observation were revised to match the safety standard of deep mining operations, not because the data lacked value, but because the cost of obtaining it was no longer abstract. Each descent now carried a measurable risk, not just to equipment, but to the integrity of the system itself. From that point on, knowing more meant interfering more. And interference was no longer something that could always be undone. So boundaries were set, not by the limits of technology alone, but by decisions made in advance about how much uncertainty was acceptable and how much loss could be tolerated in the pursuit of understanding. The borehole remained. The measurements did not stop entirely, but they were no longer driven by curiosity alone. They were constrained by responsibility. And that left a different kind of question behind. If measuring the Earth can itself become a source of risk, where should science choose to stop? And are there places that should remain not unexplored, but intentionally unmeasured?